I think AGI is a fighter jet and GPT-5 is the wheel. So like it can help you get going, but we still need to invent the jet turbine and the parachute and all those different things. Like a toddler can understand that applesauce is sweet without learning the word applesauce. As we're building AI right now, it has to start with the word applesauce and then relates applesauce to all other words. That's not how we as humans and intelligent beings operate.
Anyone who's coded with these LLM tools, you eventually hit a point where it's kind of just refeeding bad ideas.
Yep.
It'll start looping and you'll like fix a problem and it'll create the same problem that you just fixed.
Yep.
And then you get in this loop of regression. And it's due to the memory thing, but to your point too, it's also the limitations of the model eventually bear out. All right, today we are joined by Ian. Ian, where does the podcast find you?
Hi, yeah. I am Ian Hamilton, CEO and co-founder of Synthetic Cognition Labs, formerly Transparent AI. We changed our name due to some interesting confusions that we had, but we're a local startup here in the Vancouver, Washington area near Portland, Oregon, and we are kind of unabashedly doing artificial general intelligence research. And so that means we do like cognitive science, modeling, perception, memory, and things like that. And I'm just here to talk with Andrew about what we're working on and what his thoughts are, and hopefully educate some people about non-LLM or neural network AI.
Yeah, that's awesome. I think before we get started, I've been on a rampage against AGI because I think there's so much hype right now and it's so oversold, and it's just like, we're on the precipice. We need $100 million. We need 100, so everyone's using it to raise. How would you define AGI? And like, how would you know if we got it? How do you know if you succeeded?
Yeah, so actually this is a great starting point. Yeah, we were pitching to an investor like 2 weeks ago, and they were using that as one of their like stage gating questions for AI companies. Like, oh, everyone assumes that AGI is inevitable at this point. It's going to be here within the next 3 years or guaranteed within the next 10 years or whatnot. And he said that I was the only person that they've talked to where I was just like, abso-freaking-lutely not. I don't think anything like what we have now is even remotely close to what we have in our idea of AGI. I think the LLM tools are helpful. I saw a post a long time ago, and I think ChatGPT 3 came out, that was like, if AGI is a car, ChatGPT 3 was we invented the wheel. And I think it's even beyond that now. I think AGI is a fighter jet and GPT-5 is the wheel. So like it can help you get going, but we still need to invent the jet turbine and the parachute and all those different things. So the like definition of AGI, from our perspective, we try to look at things like, does it genuinely start to replicate some of the cognitive or intelligent functions of the only other intelligent being that we know of, humans. And as far as we can tell, if you're like looking at some of these LLM tools or things like that, they so far miss the mark. There's no, I guess, quote unquote, like outside the box thinking, obviously, because they're just trained on what already exists. I do think actually some of the puzzles, like the ARC AGI prize, which is like a visual logical reasoning puzzle, some of the best models still only get like 25% on them and things like that. And I think we're a far cry away from seeing something that can truly incorporate like perceptual grounding, so not language grounding, like actual vision, sound, senses as the definition of what its knowledge base is. Right? Like a toddler can understand that applesauce is sweet without learning the word applesauce. As we're building AI right now, it has to start with the word applesauce and then relates applesauce to all other words. That's not how we as humans and intelligent beings operate. And so, perceptual grounding, continual learning. Most people don't really know that like these neural network based LLMs, they train them and the model itself is static, cannot continually learn. And so that's why OpenAI and Anthropic and whatnot, they got to spend like hundreds of millions of dollars like every couple of months to retrain the newest and best model and things like that. And it's not, you don't get to just train on the difference. You have to start over from scratch. Like you have to train the entire
Yeah, it's
model
like
over again.
non-modular.
Yeah,
It's
it's
like a
non-modular.
one and done kind of
Yeah,
thing. Yeah.
yeah. So there's one thing that like has really caught our eye for the technologies that we're working on. There's a lot of cognitive scientists that think like analogy is
Hmm.
the fuel and fire for thinking.
Interesting.
It's a book
Yeah.
by Douglas Hofstadter, and it's the ability to kind of do this like relational outside the box thinking and combining similar ideas, learn something in one area, apply that to a different area or whatever. The current AIs and LLMs and even the base neural network architecture is actually very bad at that.
Right.
And so that's one of the reasons that we've picked some of the stuff that we're working on, because it's very good at that. And
Hmm.
so I think that's it's kind of one of those things where it's like hard to define up front, but
Yeah.
it's for me easy to tell what it's not, I guess, right?
I would
So
absolutely agree with that. Right. It's like kind of what you were saying. If you've ever learned a foreign language, it's pretty easy to like pick up words for most people or phrases, but it's the idioms. It's those sayings you grow up with that have all sorts of not straightforward, intangible meanings or inferences to, kind of a variable set of understanding.
yep,
Those are the hardest things and that's where like humor, right? It's really
yeah,
hard to be funny in a foreign language because
yep,
you don't get all those little nuances most of the time. And that's the thing that like that's the mastery of the language
yeah,
typically. And that's like the difference between like a native or a fluent speaker and someone who just really gets it. And I agree very much with I think you nailed it. It's for me is the same way. It's like I don't know what it looks like, probably because like I can't really fathom what like superhuman intelligence actually is because I'm a human.
yep,
But I know what it's not. And when I see things like a really good example of kind of what you were describing, anyone who's coded with these LLM tools, you eventually hit a point where it's kind of just refeeding bad ideas.
yep,
It'll start looping and you'll like fix a problem and it'll create the same problem that you just fixed. And
yep,
then you get in this loop of regression. And it's due to the memory thing, but to your point too, it's also the limitations of the model eventually bear out.
yep,
And the way that these companies have kind of pushed it forward is they've retrained a bigger model or a more sharper model for coding, for example, but it's a full retrain cycle. So there's no imprint of wisdom happening
yep,
as well.
yeah. There was I use Claude Code all day, every day. Opus 4.6 is
Oh, it's really good right now.
awesome
Yeah.
coding things. So I'm actually a non-technical AI. I'm a non-computer programmer. I'm a material scientist and a nuclear engineer. So it's definitely an enabling factor for me because it takes me from being able to do nothing to actually being able to talk with Claude and be like, I think this is how the brain works. Like, oh yeah, there's research that
Yeah.
shows that or whatnot. And I've got business partners that are much smarter on the topics than I am. But one of the interesting things was this, like I was talking about, like the quote unquote, like outside the box thinking or the ability to just have any type of intuition or like
Yeah.
problem solving. I was working with Claude. I had used Claude online. I fed it some research papers and like, hey, here's some weird, obscure stuff that's not in your training data. I want to try to replicate some of these algorithms. And so it
Yeah.
had built an outline for it. I took that and fed it to Claude Code. And because it's not in its training data and everything that we do is weird and out there, Claude Code like couldn't figure it out. It couldn't get it to work. And it got stuck in just like what you said, like one of these cycles of oh, maybe we should do this, maybe we should do this. And I was like, no, we've already tried that. And I could see I've got like the thinking mode
Yep.
on or whatnot. And sometimes you can see its like thought process. And it was like, oh, well, this document, this coding plan references this paper that is this title of this paper. It would be great to review that again. Too bad we don't have access to it. And
Right.
it was the paper it had done like LS and listed all the files in the thing when the project, it knew that the paper was in markdown format, the best format for
Right.
LLMs to consume it. And it went to it saw that it was in there and then it recognized that, oh man, it would be great to review the paper again. And was just like, well, too bad we can't do that. And
Right.
it was just so close. It was almost there. It almost
Yep.
went, oh, maybe I should look for the file that I know is right. It was in the directory that it was currently working in, and it just
Yeah.
could not make it that little
I
bit extra.
I spend a lot of time treating AI and like LLMs in this case like I would a toddler.
Mhm.
Like you don't necessarily want to tell it what to do, but you're like, okay, we don't, play with the stove because you might get burned.
Yeah.
This is hot, and you put their hand on the stove so they get that association. You don't burn them, but then they're like, oh, it's hot, so I'm not going to do that. And then 10 seconds later, they're playing with the stove and
Yeah.
burning themselves, right? Like, and but then the toddler eventually learns and then doesn't do that anymore. But AI doesn't have
Yeah.
that
It doesn't
capacity to
have that
learn.
ability. Yep.
And and to your point, a lot of I try to break this down for folks too. The model doesn't ever learn. So you're kind of baked in with whatever intelligence and understanding you have. And then there's a lot of clever ways that we've been faking
Yeah.
learning. And so the Claude Code or anti-gravity or Cursor, there's all these applications out there. There's a lot of really interesting techniques that they're using to try to fake memory, to try to fake learning. And it usually is okay. It usually does pretty well. But like you said, when you hit these edge cases, it just totally fails. And for me, that's the big difference between like an AGI and
Yeah.
something that's like a useful tool. Like I think an LLM is a useful tool. I think a coding agent is a useful tool. But the hammer is never going to not be a hammer. You might be able to use a hammer to chop down a tree, but it's not a great way to do it.
Yeah.
But a hammer is never going to invent a saw.
Yeah.
And it's that precipice of being able to, outside the box, as you were saying earlier, to say, well, this approach isn't working. What can I do that's different? Or how can I learn from what I've done to not repeat that again? Whereas an LLM or an AI in our current incarnation is just going to keep trying that same series
Yeah.
over and over again because it doesn't have that capability to actually to learn something and then synthesize that and then develop new training data effectively, which is how our brain works,
Yeah.
kind of,
Yeah.
right?
And that goes back to the analogy making thing. That's
Yeah.
actually why a lot of cognitive scientists think that it's like, hey, I'm working on this one thing. One of the like anecdotes that we talk about a lot is if anyone's ever had like a eureka shower thought where your like
Yeah.
mind wanders and you're working on something like, oh, wait a second, that solves the problem that I have at my day job or something like that.
Yep.
And that requires, as we were talking with memory, like true auto-associative memory. So where you can actually like things that you're thinking about recall other similar memories. And
Yep.
so like that's when we say that we're working on like the foundations of AGI or whatever, like that's one of the things that we're working on is like an auto-associative memory model.
Right.
So we built like a little demo where we can like talk to an LLM about a zebra and then fill its context window up like 10 times over and then mention the zebra again and it will automatically like recall the information.
Mhm.
And so that's like us humans, like hearing the tune or hearing the lyrics of a song and being able to pick up the song and
Yeah.
start singing it. Whereas all current memory, quote unquote, for LLMs is more like, oh, I know there's a song that's like that. Let me go Google it. Or,
Exactly.
oh, I need
Yeah.
to remember that. Let me write it down. And
Yep.
so everything has to be kind of like processed, which that is great for a lot of things. Obviously, like I have a book notebook in front of me. I take notes at meetings and things like that.
Exactly.
But that doesn't help you like recall a random one-off conversation that you had with your coworker 3 months ago that then is pertinent to a problem that you're trying to solve.
Well,
And so,
and to your point earlier too, it's also, if you use the notebook analogy, go get another notebook, but AI can't do that, right? The
Yeah.
LLMs can't get that. So they can extend their training data to a certain point by writing it down, so to speak, in a notebook, but eventually their context window will
Yeah.
then get full of notes.
yeah,
And then there's some strategies you can use to kind of do branching and that kind of stuff and like fake it some more. But you hit a wall pretty quick, especially when you're working on like large code bases or really complex, hard problems. They just fall flat at a certain point. And this is where like a lot of people I talk to in science, like they're like, this isn't helpful for me for science.
Yeah.
But to your point, it could be helpful for helping you code your science, right?
yeah,
And but that's a thing that a lot of humans don't get either.
yeah,
is like, yes, this is a tool. You have to also use your brain to figure out how to best apply it. And we were talking a little bit before we started recording. I've been seeing this more and more now. It's like the cold start problem with startups, right? It's like, how do I even get started with this? Or I need someone to tell me how to use it. And it's like, yeah, but this isn't what humans are good at. We've never really been good at like following directions. We've been really good at working in small groups to like figure out the easiest approach to solve a problem. And I always think of like one of the techniques for hunting large game in the hunter-gatherer culture is to just literally run it down and exhaust it.
Yeah. Uh-huh.
Because we can sweat and most mammals
Yeah.
can't. And so they eventually just literally pass out from heat exhaustion, or you run it over a cliff.
Yeah.
And that might sound morbid, but it's a very simple way. It's not super dangerous for you because you don't have to confront it in some kind of like battle like you would see in a movie. But that's the human mind of saying, well, we can go for hours or days, running. We'll bring some water in a container. We'll invent that too, so we can cool ourselves and replenish as we go.
Yeah.
That's what we excel at. And then we get really lazy.
Yeah. Yeah.
But AI is just like always lazy in my mind too. And so it'd be interesting. So we talk a lot about like transformers and LLMs. There's all sorts of different kinds of AI. It's basically a field of study. It's become the zeitgeist now. Everybody's a fucking AI expert or thinks they are, and I find it quite annoying. You're working on other approaches to computer learning or whatever we want to call it to avoid that AI label. Can you talk a little bit about like why those are different, or like why you think that those will provide better pathways than like the transformer?
Yeah. So we talked before we got to the podcast or started the podcast about the level of technicality that I'm allowed to speak to.
Yeah.
So I'll keep it as low as possible. But so we work with a technology called hyperdimensional computing, and it is in its fundamental form, like literally a different way of computing things. There's all modern computers, whether or not it's the ones that we're working on right now or the ones that are in the billion-dollar server racks, Elon Musk Grok supercomputer or whatever, they're all known as the von Neumann architecture. So they separate the graphics processing. Yeah, they separate the CPU from the RAM from the GPU or whatever, and they all have to talk to each other, and you get what's known as the von Neumann bottleneck, where you can't actually feed data to the processor, to the GPU from memory fast enough. And so there's this different architecture of physical computing called hyperdimensional computing, and it's actually inspired by biology. They like cognitive science researchers have actually traced the inputs for a fruit fly. So a fruit fly has like 50 analog, so 0 to 1 continuous value, like chemical sensors for their olfactory sensors. So picking up fruit smells. This is an apple smell, banana smell, things like that. They can actually trace those inputs to a neural network. They've note that the output is a 2000 dimensional, so 2000 zeros and ones, sparse binary array of zeros and ones. And sparse just means zero, mostly zeros, a little bit of ones. And so the chances of you encountering something randomly that smells the same is 2 to the 2000. So basically nothing. And what you can do is you can learn what that signal relates to. And when you go and do your computations on it, this hyperdimensional computing, all of your calculations just end up being binary, multiplication, and addition. And so the energy consumption for it is like literally like 8 to 10 orders of magnitude smaller than like current LLM models.
Right.
That's like one of the main like driving forces for what we're trying to work on. And so the idea is that you can, what's super ironic about it is in this fruit fly example, it really does seem like the neural network architecture in the brain just evolved to be an analog to digital converter, which is super ironic when you look at our computing architecture, because we have digital processors that we're trying to simulate analog systems on. And so a lot of the things that we work on, we just skip over the neural network part and just go right to the binary array. And so when you do that, you can do all kinds of really interesting things that you can't do with neural networks or LLMs. I think I mentioned the very, very low power or energy consumption in some regards, like even though our brains as humans only use like 20 watts of power or whatever, that's probably and almost certainly like very inefficient for calculating like large array binary addition and things like that. Because there's nothing like backpropagation, which is where you have to like train the neural network and update its weights and biases which is what they have to do for LLMs every 3 months. This type of thing just learns what each new vector is and learns from there. And so it can do online or continuous learning. You can assign vectors symbolic meaning. So like, oh, this vector is an apple. And then you can like assign this other vector to be an apple seed, and they will actually be very similar to each other. And so that's where analogy comes in. So you can actually build analogy-based like networks off of similarity. You could do other things like one-shot and few-shot learning. So it mimics like how toddlers learn. So you don't need to feed it 1,000 images of a horse before it starts recognizing what a horse is and things like that. So that's the like architecture that we work on. And so there's a bunch of potential benefits for like just doing things better than what the current LLM or neural network architecture has, and then even enabling capabilities that like would be physically impossible for the current architecture.
And I would say too, like, I want to keep the conversation going, but if you're not familiar with a lot of that stuff, it's pretty easily Googleable, and you can find like Wikipedia pages and stuff that'll explain it. And I think maybe a really kind of easy example of that is the current, von Neumann architecture is effectively a brute force at learning.
Yep.
And a way for folks, I think, to understand this is like, if you try to run an LLM on your like computer, on your CPU, it'll work, but it works like absolute trash because the way that the architecture is designed. It's really, really great for, I'm going to run a web browser, and now I'm going to run a calculator app, and I'm going to run some email. It's a general kind of processor with lots of different instructions built in that it knows to use. And so all those applications use it. So we got out of that bottleneck by using graphic processor units, which are more actually generalized. The big difference for those was that they're able to do different kinds of math and apply much more processing to it. And so a lot of GPUs will have 10,000, 20,000 cores, where your computer at home might have, 4, 8, 12, maybe 16. And so that also takes power, and we're pushing electrons through all those pathways on these machines, and you're doing that over and over again. And it's like, you made the point of like, what is a horse? Well, you can feed a model, a neural network model, using millions of GPUs and millions of electrons and watts, to just figure out that after seeing so many different photos of a horse, this is what a horse likeness might be. But it's still not going to be perfect, because if you show it real pictures of real horses and then you show it a drawing of a horse, it's not similar. And that's where that vectorization kind of comes into. And a vectorization, I guess, in a really simple way, is just kind of computing what something is mathematically, and then you can compare that to another computed vector. And then you can look at how different they are, and then that tells you if something's similar or not.
Yep.
And a lot of the LLM stuff, I guess, to use really general terms, works this way as well. But because you have to do all of that math and you're brute forcing it, you're literally, it's like anyone who's done long division, you're starting with this massive number and you have to go by hand and do it all. The computer can do it much faster, but the computer still has to do that every time. And what you're talking about is the ability to either kind of intuit in that model just in general, or change the approach of how you come up with those vectors and leverage those vectors. Right.
Whereas the LLMs and neural networks have to learn through large amounts of data, this type of thing learns through memory. So there's this another high dimensional technology that we use called sparse distributed memory, and it stores these vectors, what's known as content addressable. So where, depending on what the thing is, similar things will be stored like physically close together. So like if you had like a computer chip or whatever, like that was your actual memory substrate, like, and you fed it like a vision model, like all vaguely round and red things, stop signs, apples, Volkswagen bugs, beetles or whatever, would be physically stored close to each other. And so when you do this, you can have like a novelty threshold, which there's actually some interesting cognitive science research on like infants and toddlers and things like that their novelty threshold is like crazy low just because everything is novel. And so like if you've never seen something before, you're like, I don't know what that is, but I'm going to store that vector. Oh, hey, look, it's vaguely in the same area as this other stuff. And so that's again where it comes back to this like analogy making. And what's really interesting about it from the kind of like as you got back to like the what is AGI or what are these tells for AGI perspective or whatever, a lot of the standard parameters that we use for these models that we're working on, just people just pick like 10,000 as the length of the vector.
Mhm.
And the reason they do that is just because like the chances of any two random vectors being similar is going to be 2 to the 10,000. It's
Yeah.
crazy improbable. But your capacity for how different or how similar your things are to each other for learning and growing and things like that and making analogy is directly tied to the size of that vector. And
Mhm.
we can do like physically, like right now, and there's research out there, there's Wikipedia articles, there's published papers. You can do really cool things with this technology at like a vector size of like 10,000.
Wow.
There's some neuroscience suggestions that like the brain operates on vectors of like 100 million. And so now
Jesus.
you can like you're comparing things to other things
Mhm.
and like you're doing like you can get like deep into it of like what neurons are physically firing or on at the same time. And I think like the whatever the estimate is that roughly like 80 to 100 billion neurons in the human brain or whatever. And so you're trying to figure out like temporally which ones are on at the same time, and if your vector is made up of the ones that are on, it's millions to tens of millions to hundreds of millions. And if
Right.
that's your capacity for analogy and problem solving, quote unquote, as like another way, if we can do cool things on my computer right now with a capacity of 10,000,
Right.
they're like think of the cool things you could do with like a capacity of like 100 million vector.
Yeah.
Unfortunately, when we get to that scale, that's where custom hardware comes in. You
Right.
need custom hardware for that.
And I think for to try to make an analogy for that point, it having all of the vectorization of things done and the ability to interconnect those is how we synthesize. So like we go
Uh-huh.
through the world, we know nothing,
Yep.
we touch things, it's hot, we have our senses, we taste things, it's salty, it's bitter, and you build all those associations. And so if you've ever eaten a food dish from another culture that you're maybe not super familiar with, you're like, it kind of looks like noodles and some kind of meat.
Yep.
You have some sort of an imprint that you've had pasta and you've had all this other stuff, so you can kind of suppose what it is. Most of the time it's probably going to meet that. Sometimes maybe it's just totally out there because they're using spices that you've never encountered, but you'll know what that spice is and you'll be like, oh, this is a spice I've not encountered before. The LLMs and the current way of kind of processing that is we have to build the model of like what is spice,
Yeah.
and then we have to build the model of what is taste and what is bitter and what is salty every single time effectively. And kind of going back to what your training comment was, so every time we do a model, now we have to reprocess all of those
Mhm.
inputs based on what we call weights, and there's some other stuff that we do, and then we can maybe push it a little bit further. But again, it's not really learning, because once that model say it gets 10% bigger or better, however you want to quantify it, that's it. And then you do it again and maybe you get another 10% or maybe you get another 2% and it gets a little bit better, but it doesn't have the ability to like think outside of its own
Yep.
model. And that's where these different approaches are very fascinating. I'm trying to think how to ground a little bit more for folks. Are there current examples of these types of architectures that are like kind of easy to grok for folks that you can think
Um,
of like where you would see it applied? I can't
no,
think of
it's
anything offhand.
no, it's all like the closest thing that even remotely comes to it is RAG, retrieval
Sure.
augmented generation for LLMs, because they turn like documents into vectors to try to find similar type things. Technically that's kind of like the same process, but they do it like as a post hoc thing. We do it as
Right.
like the main thing.
And you're
But
still translating the document into vectors and then
yeah.
storing those vectors in such a way where it's almost like a non-vectorized storage, because you're storing the value of the vectors and not necessarily in like a three-dimensional space. It's really hard to talk through this on
Yeah, it is.
camera,
Yeah,
but
the
I, I should maybe try to find a visual to like put in the
Yeah.
video for folks, because I think once you kind of see those models, then you're like, oh, it's like 2D versus 3D almost, right? You gain a whole nother dimension
Yeah.
of interconnectivity that you just don't get with like a vectorized database with a RAG or something like that.
Yeah, yeah. The differentiating factor is kind of like the granularity and so none of the RAG databases or anything like that are what's known as compositional. So you can't like take two vectors and smash them together to get a new one or whatever. The types of things that we work on are, so like some people may have heard about like tokens and how many tokens LLMs can process and things like that. And that's taking like individual English words and breaking them up or using the entire word and then turning that into a vector for something to learn. The types of things that we're working on and eventually want to do is like getting down to like what does the letter R like physically look like feed it into an image model, turn that into a vector, and then label it R. And so then when you go ask the question of like, how many R's are there in Raspberry, which if anyone knows was a thing that LLMs got wrong for a very long time.
It's between 0 and 7.
Yeah, because of the way they actually tokenize and split up the word. It's more like, oh no, like I recognize the R's in there. And so, and like R and A and S and things like that form a collective word. So you're taking these individual vectors from letters and combining them into words that are then also bounded by visual cues and things like that. And so it's like you said, like this one kind of this extra dimension. You could almost think of it like each level of perception is an additional dimension that you could kind of do. So like actually the taste like chicken example that you just mentioned, we literally just put that into a paper that we're working on where we identified like we fed it like an image of an apple, an audio recording of someone saying apple, and the text of APPLE, and then combined all those together. And because it's content addressable memory, like you can show it another different picture of an apple and it will recall the word APPLE and the voice recording of apple. And so you build up these like concepts of how all these things are related together, much closer to like, again, just going back to like how toddlers learn, like you feed it applesauce or like in a picture book, like this is the letter A and things like that. And so you're learning these things at a much more granular, more grasping the true underlying concepts rather than just take an English word, turn it into a vector so that we can look it up easier or something like that. So that's the main kind of like differentiating factor between that. But outside of like RAG, there's actually not a lot in this area. There's a bunch of research on it. We often get the questions of like, well, if this is so great, why isn't it around and whatnot? There's not a terribly easy answer. I even like keep a notepad in front of me for that answer. We've talked to researchers that like abandoned it prematurely, like in the early 2000s, because they thought neural networks were going to be the be all end all. We've talked with researchers that didn't abandon it and couldn't get funding after 2017, which is the attention is all you need paper that basically created the modern transformer architecture. And then we've heard, I know I told you this at the meetup that we had met at, we have heard an anecdote that maybe it does work very well and maybe a little too well. We've heard through the grapevine that a certain cell phone manufacturer and a certain computer company teamed up to do this a couple years ago, had some success, and scrapped the project because why would you make a phone that has a 2-year-long battery life off of one charge and a borderline supercomputer for computing in your pocket? You'll never sell another phone again. So and we've told that anecdote to some people, and there's a lot of people that have been like, oh, yep, that tracks. That's 100% sounds right. So
in the investment space specifically, the von Neumanning, using a different architecture then requires you basically reinventing all of computing if you were to just like put that in a laptop, right? And so a really easy way for folks to understand this, or maybe not easy, but an easier way would be to look at like the different architectures between, you have Intel with the x86, x64, you have ARM, you have RISC, there's a couple other ones out there that are somewhat common in certain industries or certain settings. You have like the Power architecture that IBM famously keeps alive somehow, which is also starting to come back again with because of the RISC basis. It's actually much better at vectorization because it has shit, this is going to be a little bit of a tangent, but like one of the reasons Apple back in the day went with the G3 to the G4 leap, there was a 128-bit processing engine. I think they called it Altivic, and it's a vector processor that's embedded on the chip. And so computer graphics, video editing, all this stuff can benefit from vectorization because you're effectively just pushing stuff around the screen. And if you get really clever with how you do it, you can get massive performance gains by offloading all those calculations to this special processor. GPUs kind of beat it out though, right? Because they became cheaper, more ubiquitous. You could also use them for things like games or videos or 3D space. And so there was more uses that people were able to use for them. But they're starting to come back again because that architecture now is basically free.
Yeah.
And I was just reading a thing where there's an open source RISC product that is getting like, I think it's 40 tops of performance on just, I think it's like 65, 70 watts of power, which to try to like bring that to folks, if you run an LLM on that, you're probably getting like 1 to 5 words a second on like a relatively decent sized model. But the fact that that happens in like 60 watts and like works is phenomenal in a lot of applications. And so that's, I think, kind of like what you were saying too, is like people don't just do stuff because they can. A lot of times you have to have funding if you're in academia, or you have to have commercial sponsorships. If, the thing that you're building kind of obsoletes the technology that is making you money, there's always a lot of conflict in companies or even in academic circles. And so that is a very real possibility. And it's also, I think too, that like you said, there was kind of this perfect storm of like these neural networks were really starting to gain traction. Computing was getting pushed forward. It was following Moore's law, so it was getting cheaper. And so it just, this entrapment of the technology we have is good enough. But now I think the constraints of like the power in the data centers, the cost of just NVIDIA chips, like NVIDIA is pretty much the only supplier of the chips that you can train stuff on. Like there are other options, but they're smaller scale, or they're more suited for either pre or post training or different parts of the pipeline. The nice thing with the NVIDIA chips is you can do all of it, right? Like it doesn't do it all super well maybe, but you can throw anything you want at it and it'll do it as long as you get the electrons.
Yeah. Yeah, we liken it to like fossil fuels and clean energy, basically.
Yeah.
Like we had batteries and electric motors and things like that, like 100 years ago.
In the 1900s.
Yeah, in the 1900s and whatnot. And it was just that like we started down the oil and coal path and got so entrenched and ingrained in that, and there wasn't any like immediate massive need. No one had really figured out greenhouse gases or global warming, that like, hey, this is a doomsday type scenario. Maybe we should look at the alternatives. Type of thing. And so they just did that. They went down one path for 100 years, well, more than that. And even though there was this other branching opportunity that could have been started like 80 years ago. So like, even though like, some of our pitches to VCs are like, hey, if we're successful, all of your other investments won't be, type of thing. But for some of the potential, everything from environmental impact of these LLMs and whatnot to full on like global economic collapse of AI bubble popping and things like that, I don't think we can afford to do the 80 years down the LLM neural network path before we start exploring other things, like even if it does require starting over. Like I think I mentioned, like to get some of the really cool properties for the technologies, like we would eventually need like our own custom chips, like our own custom hardware silicon. There are some products that are out there now that we want to buy. They're like research and experimental and things like that, but it's like $250 to like plug a different type of architecture into your PCIe slot for your computer and things like that. They're pretty low capacity for calculation and whatnot, but so there are people like exploring that and driving that in the non von Neumann and things like that. So, but it is a pretty tough sell when we're like, hey, everything that you know and love, we need to nuke it and start over if we want to get the true benefits from. That is one of the things that we're exploring recently. I mentioned before we started the podcast is that we're taken a tiny little diversion from our nuke everything plan and start over to like, can we just make current LLMs better? And so
Right.
we've worked on like replacing the transformer architecture, replacing all the neural networks and things like that. And kind of through some like happy accidents, it's actually working. And so our pitch or business model or go to market or whatever you want to call it for our research is that we get to use the cool, like, energy efficient, small, compact model like technology under the hood, but still turn it into an LLM, and then it still runs on NVIDIA GPU clusters and things like that as kind of like a stepping stone, like a bridge the gap type of thing.
Right.
And so like, yeah, one of the things that we did, we made like the model like 5x smaller and still got like 80% of the performance and things like that. So
That's
and it looks
awesome.
like even then that can be like fixed and maybe even improved to the base performance and whatnot. So this like method of computing itself, you can like emulate it on a GPU to try to get like kind of started essentially. And so you don't get the full power and energy benefits of like a custom hardware, but we're trying to think about like, hey, maybe we should do that as like a stepping stone, or needing to raise $1 billion to make our own foundry.
And that's what we, yeah, and that's what we used to do. And, you know, I remember like Sun Microsystems used to have like network accelerator cards that were effectively crypto accelerators to do all the math for cryptography, so that you could just like plug into your existing network with all your dumb switches and stuff, but then accelerate the shit out of those loads so that your server didn't have to do all the computation to
Yep.
actually understand that was coming in and out. And then your server could do all the computation for serving the web page or
Yep.
whatever, batch the job or whatever you're trying to run. And then all that stuff just got baked into the network controllers and stuff over time, and things got smaller and cheaper, et cetera, et cetera. But I mean, I remember those cards used to be tens of thousands of
Yep.
dollars to get, you know, like what we would now consider today just like absolutely ludicrously slow acceleration. But at the time it was groundbreaking. But to your point, it was an add-on to an existing
Yeah.
technology, and then we improve the technology, and that's like a strategy, right, to get out of this like innovators gap
Yeah.
problem.
Yep.
And so that's really awesome. And I guess for folks too who maybe are totally lost at this point, you can always pause in Google or use an AI to help you navigate information to a certain point. But it's not dissimilar, it sounds like, to like quantization of a model, except for it's more of a like native speed, and you don't, by quantizing you lose a lot of capabilities, whereas you're basically just offloading via vectorization. You get a speed, and you lose less information because you're not truncating the amount of information you have. You're just changing how it's processed, right? Like effectively.
Yeah.
high
So that's
level.
basically that's how this little kind of side tangent project started. We were like, well, it's called LLM, like you said, quantization or minification, where you try to make it smaller and use less power, less parameters, and try to keep the performance same or whatever. And they've certainly had like a bunch of luck with that, and like making the precision smaller and doing like, what is it, 1.6 bit or something like that. And so we're like, oh, could we do that with our weird like technology or whatnot? And yeah, it looks like we can. And so like you can get this, it's like a different method of compaction or minification, and you can do these weird strategies of like data compression and compute and things like that you can't really do in the kind of this normal distillation or quantization or minification process.
Right.
And so we're trying to, our end goal is to like make the models smaller, faster, less energy intensive, and improve performance. We've actually have some experiments that show that maybe that is, we took our architecture and took a standard transformer architecture and compared the outputs from each individual layers of the LLM. They were nothing alike. They were wildly different. But the final score of our LLM versus LLM was just a little bit behind the normal one. And so what that tells us is there are different or better ways of finding the same patterns or computing the same things than neural networks can actually find on their own. And so there's like a little bit of hope there that like, wait, can we actually improve performance? Could we make like Can we make
Right.
GPT-5 like 10 times smaller and give it better benchmark scores on LLM performance and things like that? So that's kind of the grand goal and vision for this little side project.
Yeah, and for folks at home too, the idea with like quantization, just like a really hopefully easy example is like if you go from 8-bit precision to 4-bit precision, that's roughly half as much. But the reality is when you run it, the GPU or whatever you're using to power it still has to do that math. And so like I'll just make up some numbers for illustration points, but 4-bit math, let's say, is about twice as fast as 8-bit math on your GPU. So you theoretically get double the performance, but you're still using the same amount of power. It's not a one-to-one, so you actually do lose some processing power on your GPU. But more importantly, a lot of times you lose half the precision of
Yeah.
your model. And if you're just asking for general stuff, it doesn't typically come through. But that's the difference between like understanding a very complex object class in a code and not understanding that, or being able to like follow the code enough to like do it, or to give you a deeper understanding of a research proposal that you're having the LLM help you with. It'll give you, you know, more general feedback, or it'll give you much more varied feedback and
Yeah,
not as
varied
accurate
is the
feedback,
yeah.
are kind of the trade-offs that you have for those approaches. So again, if you can figure out a way to keep that precision, but then train it in a different way or run it in a different way, that's kind of like what you were saying earlier. You can get, you know, 10x maybe less power for roughly the same performance. And, you know, if it's 90% is good, 95% is good for most people, that's probably more than enough.
Yeah.
And these are these trade-offs that I don't hear a lot in the AI world. It's like we just are given these models by these three companies and we're just expected like this is all that's out there.
Yeah.
There's all sorts of companies doing all sorts of different techniques, and like DeepSeek is one where they came up with a different training process that required much less compute to run the neural network and train the neural network, which brought through a big breakthrough that then everybody copied.
Yeah.
But they had the constraint of not having the compute available because of limitations of the government or whatever the embargoes were.
Yeah.
And so this approach that you're taking, I mean, it maybe sounds crazy to some folks if you're not really deep in the weeds on it, but it's very, these approaches are happening all the time. But the difference is like this is just a totally different way of thinking about computing than what we've been thinking about computing for probably 60 years, give or take. It's not unheard of. There's all sorts of other architectures out there as well that run in computing world that we don't really talk about because sometimes some of them are classified, but some of them are just so exotic and foreign that they're solving such specific problems. Like ASICs come to mind that, you know, everybody kind of gets what those are in computing, but to actually apply them is very difficult.
Yeah.
Go ahead.
Oh no, I was just gonna say, yeah, if people have heard of like the quantum computing, like it's literally, it has the word computing in it, but it is fundamentally a different way of doing math and calculations. Like it's entirely different architecture and things like that. And so there are things like that. There's actually some pretty interesting startups doing like analog computing where they're doing everything with like resistor calculations and analog math and comparator circuits and things like that. And so it does entirely different form of physical hardware to do either the same math differently or an entirely different math, and it broadens what you can do. We just got entrenched in the von Neumann architecture, just like started to work, and then when we were building like computers, it was like for office machines and for the international business machines, or for like trading desks, and like stockbrokers were some of the first people to have some of these high-end super expensive computers back in the 70s, and that just like stuck and worked. And so we never branched off, even though there's been all these other options and things like that along the way.
Yeah. And in my understanding, and it's been a while since I was in the balls of computer science this deep, but the von Neumann architecture translated really well to integrated circuits.
Yeah.
And it was one of the cheaper, more mass producible architectures at the time. And that's one of the reasons it won out, because it was just cheaper.
Yeah.
And if you look at, you know, the history of computing, like there's no reason we all shouldn't be running around on RISC machines right now, because it's frankly probably a better architecture. But it was for all sorts of weird reasons. And then also somebody patented some stuff
Hmm.
and then pushed it out to the whole world, and how Intel is, infamous for computing, but they basically monopolized the market for better or worse. This isn't conspiracy shit. This is just what happened.
Yeah.
And they like the X computing comes to mind too. Like that was a fantastic system for high scale, and like Spark even was a
Hmm.
really interesting adaptation of fundamentally RISC and some other stuff. But again, it was really expensive, but it would really, really, really performant. But then we found that if we just had a bunch of really, really, really cheap CPUs, and even if they died occasionally or went offline, we just had so many more that we could scale the cluster, and this is, where you get these like grid level computing ideas from, whereas the giant server that you had wasn't really necessary anymore. And then there's some other pretty poor decisions in the end there, but the rest is history, as they say.
Yeah.
So we've talked through quite a bit of stuff. Is there anything else you wanted to talk through? I'd love to have you back when you're done with the LLM experimentation, or learn
Oh,
more about it. Because I think I try not to talk about AI all the time, even though our weekly with Nathan and I, we talk quite a bit about AI because people seem to be really interested in it. But I've gotten really bored with the conversation because we're just talking about different ways of like rehashing the transformer architecture. And I've told people, go back, read the paper. Like you do need to know a little calculus, but like it's not really that hard of math even. Like the core of the architecture is really not that like interesting, I would say.
Yeah.
It's really interesting at scale, and it seems to scale very well to a point. Like I think we're hitting that point, and I think we will hit it soon if we haven't hit it. But it's one of these things where that's why we're throwing more compute at it, more compute,
Yeah.
more compute, more compute, right? But we talked a little bit about this before too, but we're monoculturing and like monopolizing the idea of the only way to have AI is more compute, but there's
Yeah.
all sorts of different approaches. And that's one thing when I initially met, like it's like, oh wow, finally someone's talking about some, and there's a lot of people who have crazy ideas on this
Yeah.
stuff. And like what you're talking about isn't crazy, it's just not common, right?
Yeah. The like different ways of going about it, and I get really frustrated by the scale like argument. There's actually I knew a VC from my previous startup that had done AI stuff and had done a blog post. This was years ago, I think like 2 years ago, where I had been talking to him about cool out there AI ideas and things like that. And he had done like a LinkedIn post about like, oh, they are an AI VC, but the future of AI is scale. So like they are
Yeah.
like, and
They've already bought into the solution.
no other solutions, no alternatives. So they were like making an announcement that they were no longer
Yeah.
looking at like even like LLM wrapper companies or like AI companies or R&D or whatever. They were investing in like, they're an AI VC investing in like power electronics for GPUs. So
Yep.
like that was their idea of being an AI focused investor, of just like the only answer is scale. Scale is the rate limiter. We need to scale everything as much as possible. So if we're an AI VC, we need to invest in like a new breakthrough in like silicon carbides, like power transformers or things like that. And that counts as an AI investment to them.
Yep.
Even though it's like a fundamental like hardware technology investment. Like I wouldn't call that like that an AI VC should invest in that. But it was just, it took me, like, I knew the guy pretty well, and I would not have thought that he would have kind of like fallen for the scale hype
Yeah.
and things like that. And they pivoted their entire like multi-$100 million fund, AI
Yeah.
VC fund to it.
Well,
So
the problem is it does work. It's just diminishing
yeah,
returns, and
yeah,
and it's also a very similar model to like software and SaaS companies, where it used to be in the early 2000s, you were a startup if you had 100 servers in a data
uh-huh,
center somewhere, because you could figure something out with it. And if you could run stuff at a scale, then you could get more customers, because the big limitation at the time was really just like your server just can't keep up with more than 100 customers or
yeah,
something. And
yeah,
so we've spent 20 years figuring that out. And then once we kind of solved hardware for the most part for SaaS, or software as a service, Then it was, how can you scale like a Facebook to, hundreds of millions of users at a time? And everyone was, you wouldn't get investing unless you were going to go after the global market.
Yeah.
That was a big thing for a while too. And the reality is most companies never hit that. And most companies are really not needing to solve those problems. And the companies that are solving those problems are solving them in very specific ways, even for scale. Whereas what Facebook is doing, like the graph technology that they've built, doesn't really work for most problems outside of massive billions of things happening very fast. And it's not, that's why they open sourced it, right? It's like, it's cool. And I've actually had to apply that at scale before it does work really well for some certain problems, but the problem set that it's actually good for is very small.
Yeah.
And so that's where I feel like, and I think I've lamented on this on the podcast before too, I feel like technology has gotten really boring in the last like 10 years, right?
Yeah.
Because I remember when I was younger and was kind of getting into this stuff and through, kind of my mid-career, there's always someone coming up with some new crazy way of doing something or the UI, but it's like, even when you go build an app now, it's like, well, if you don't have the like hamburger menu on the top left of your app, then it's not a good app. And how am I going to figure out how to navigate it and all this kind of shit? And it's like, well, you don't want to just break something that works because it works, but maybe you're trying to do something different, and we need to encourage that more. And that's what a lot of this podcast is about, right? Is encouraging different perspectives, because none of this stuff ever got here because someone had a singular idea and then made it happen, right? And von Neumann specifically, he wasn't even really in computers. He was more into math, and he was trying to solve logic problems. And it just so happened that logic problem printed on a circuit pretty well and scaled cheaply. Yeah. So is there anything else that you want to mention that we haven't talked about, or is there something I should have asked you that I didn't ask you?
I don't think so. I think we covered most of it. Yeah, I'm happy to come back and chat later on. I could go off on a whole other tangent about something that you just mentioned about like just like research and development for progress. I think hasn't really been the same since essentially like the Manhattan Project, because we had like a goal we had to do this thing or else we were going to lose the war or whatnot. And now a lot of the academics and academia or whatever are more doing research like to get their citation or their publication number up, not for doing research to produce anything that's beneficial to society.
Break something novel out of the established pattern of funding, right? So it's like I research, I'll just make something up like green bugs because I will not get funding if I research red bugs.
Yeah. Yep.
And in a lot of academic areas, it is that ridiculous.
Yeah. Yep. Yeah. So I have had that complaint and that kind of like philosophy of like, well, especially like how did we get here with like the neural networks and stuff like that? Is like, well, they were theorized like in the 1940s and like late 50s or whatnot. And then you had people researching them and that got funding. And then those PhDs became professors, which then they each had their own 100 PhDs. And then the network effect came out. And so that's how you have this ubiquitous thing of just like doing research for the sake of doing research, not necessarily doing anything. Well, there's for the benefit of the mankind or civilization or whatever, or there's for the benefit of capitalism, really, because most of the original like AI and neural network research was funded by like ad companies because turns out it was really good at like predicting who was going to buy what, when, and how, and things like that. So, but yeah, there's a lot of like, especially some of the stuff that like the weird papers that we're researching or finding or whatnot, that just like kind of were like dead ends. And it was like, hey, that was like a really good idea. Like that paper is amazing. It's from 2014. Where did you go with that? And someone like the professor that we were talking to was like, oh, that research was sponsored by the National Science Foundation. And they chose to not renew the next phase of our work. And so we just abandoned it all. Yep. And it was like, that could have been like the groundbreaking technology, but it just was not. It wasn't green bugs, like you said. Like it wasn't the thing that got funded.
Or it's not obvious what the application is. And I know some people talk about this as well, but I've talked about it on the podcast a little bit. I've had some scientists on. It's always hard to fund like the null case or like the things that don't necessarily look like they're producing results. But like we would have never had antibiotics had some guy not done his dishes over the weekend and then said, maybe I should look at this and see what it does. Yeah. And maybe I'll experiment with this. Is a weird color mold, right? Yeah. Like and that's how we got penicillin. And like there's a lot of theories of like antibiotics before that, so he wouldn't just come out of nowhere, but like we didn't understand any of it. And I don't remember what actually spawned it, but I think it was something about how the pattern of the mold
The
was like
mold grew around.
repelling
Yeah. Yeah.
something, and he was like, that's weird, like why is there a barrier here?
Yeah.
And so there's this serendipitous stuff, but like you can force that in an innovation machine too. And what I've found in the last 30 years of our country is we've shied farther and farther away from audacious bets or funding people who have ideas that are outside of what the main narrative of stuff is. And I talk about this in terms of creativity all the time too. And I feel a lot of times like a lot of stuff is just more boring.
Yeah.
And everyone's like, you're just old. And I'm like, well, yeah, I am old, and I'm like learning. And I've, we were talking earlier about how you build all the patterns. I've built a lot of these, patterns up in my brain over time. But as a society in general, we're just doing a lot less interesting shit.
Yeah.
And a really easy example of this too is like going back to the moon.
Yeah.
Everybody's getting all fired up for it. I'm like, we've already done that. And I think the more interesting thing is we still don't know how to get back. Right? We've had to reinvent a bunch of stuff for rocketry because we either pushed all these people off the project to different stuff, or they died, or whatever, or we burned it in the archives, or whatever the problems were. But we're effectively having to reinvent technology that we had in the 60s, in the 70s, and we're having all sorts of problems. Like I just read this morning that the helium leaks are like scrubbing the test mission to fly around the moon now until maybe April or May or June.
Wow. Yeah.
And I don't want to like diminish the work of from what I understand, working with helium is like dreadful.
Yes, it is.
Or was it hydrogen? Yeah.
Both of them, hydrogen and helium. Really tiny atoms squeak through things very easy.
But at the same time, the interesting thing I think that came to me in the article was that they've been plagued with issues from day one. But I'm sure somebody said this is the technology, because we didn't use that technology to go to the moon the first time. There's reasons, I guess, now they're using it. I don't know. I don't get into all the details, but what I want to see is where's the second bet for getting to the moon, right? Because we've come to this, our society has very much come to this notion of like the hero bet, right? So it's like all of our movies have like the hero.
Yeah.
Well, there's other ways to tell stories that don't involve one person having some superhuman ability to solve all the problems. But that's what we're really into now. And that's what is translated into our society of like, there's only one way to get to the moon. There's only one rocket type, even though we had a type that we've forgotten how to make.
Yeah.
And so I just want folks to kind of think through that a little bit too, as you're digesting what we were talking about. And I want to see a change. That's part of why I started the podcast. So I really appreciate you coming on. I'd love to have you back in a few weeks or a couple of months when you have more to share. And I think this is a really good foundation for folks to kind of understand something that's not in the same vein of what everything is going on. And so hopefully it'll be easier for folks to kind of catch up next time.
Yeah, hopefully. And I'm happy to, I don't know if you're going to post any contact information or anything like that, but happy to answer questions or talk to people or whatnot. We got our website up. It's just syntheticcognitionlabs.com. Ian at syntheticcognitionlabs.com is the email. And I'd love to talk with anyone that's interested and love to come back and chat more.
Yeah, for sure. We'll put all that in the show notes for folks too.
Awesome.
So awesome. Thanks so much.